review your test after the lecture. So today we're doing 2.3 and 2.4. Up until now, we've been taking limits, but we've kind of just mostly been relying on your intuition as to what limit is. So 2.3, we are now going to introduce you to the precise definition of a limit. We're going to tell you what exactly a limit of a function at a point actually is, rather than just relying on a picture and our intuition to tell us what the limit of the function is. Now, before I introduce you to this definition, and here it is, this is the big bad definition of calculus. This is the thing that if students are struggling in calculus, it's pretty much always and forever with this definition of a limit. Because as I told you, continuity, it's going to be related to limits. Derivatives, they're a type of limit. Integrals, they're a type of limit. And so you've got to master limits if you're going to master the rest of calculus. Everything comes back to limits in calculus. So there's a big bad definition. We'll go over it. But first, let me try and prime your intuition to try and make it just appeal to you a bit better. So we're going to start out by playing a game. Here's a game that we're going to play. I've got some function over here. This is the function f of x is equal to 2x minus 1. And we're going to look at how this function behaves around the point c equals 4. So we've got our function. Here it is. C is the point in the x domain where we're going to look at this function. That's all we're doing so far. Okay. Now, here's the question. We know at 4 the function spits out 7. Let's say now that my question to you is, I want to be able to wiggle around 4. How much can I wiggle around 4 and be ensured that my output will still be within 2 units of 7? So we won't go higher than 9, we won't go 9 or higher, and we won't go 5 or lower. So we want to stay within 2 units of 7. How much can I wiggle around 4, and for sure my mapping is still within 2 units of 7?
One on each side, so 1 unit.
So you're intuitively seeing 1 on each side. You see 3 would map up to 5, and 5 would match up to 9.
Yeah.
So as long as we stay between 3 and 5, if we stay in this interval and we map it up through, then we would stay in that interval.
Yeah.
Right? Now, the name of the game is going to be, you don't have to find the biggest interval that completely maps into there. You just have to find an interval. You happen to find the biggest interval. You could have also used from 3.5 to 4.5. Used a smaller interval around 4, and that still would have worked, right? Now, let's derive what you did. You just looked at it pictorially, used your intuition. Let's go through the algebra for how we would have actually derived this. So here's now the algebra. We want the distance between our output and 7 to be less than what number? 2.
Yeah.
We want our outputs to stay within 2 of 7. Right? So, absolute value of a difference. Sorry, what?
Is it less than or equal to, or just less?
No, less than. We want it within 2 units, not including 2. Now, the absolute value of a difference gives you the distance between those two numbers.
Yeah.
That's what it gives you, intuitively, right?
So why is it minus 7?
That's going to be the distance between these two numbers. What's the distance between, so for any two numbers A and B, A minus B gives you the distance between them. Give me a number.
6.
6, give me another number.
7.
Well, let's say negative 7.
Right.
Keep it more interesting. Well, we could have done 7. So 6 minus 7, what's 6 minus 7?
1.
Negative 1. Now take its absolute value. 1 is the distance between them. What's the distance between 6 and negative 7? So you would do 6 minus negative 7, and then take the absolute value. What's 6 minus negative 7?
13.
Positive 13. Positive 13, absolute value of positive 13 is 13. And so it gives you the distance between them.
Yeah, but why can't you do f of x plus 7?
That doesn't give me the distance between f of x and 7.
Well, it's
I want to keep the distance between 7 and the output of my function within 2. I'm looking for all the outputs of my function
Yeah.
whose distance from 7 is less than 2.
Whose distance from 7 is less than
Yes, so here's our function. F of x equals 2x
yes.
minus 1.
Yes, okay.
We're looking for our inputs that we can plug into this so that our outputs are within 2 units of 7. So I want my output's distance from 7 to be less than 2.
Okay, yeah.
So it has to be a minus there. Now it doesn't matter that I wrote f of x minus 7 versus 7 minus f of x. Those evaluate to the same thing when you take the absolute value.
Yeah.
So there we had some choice. As a matter of convention, we write it this way.
And then the constant, the c for 2 can be anything.
The c here is the point we're focused around.
Yeah.
So I'm looking at the function f of x equals 2x minus 1 around the point c equal to 4. The question is, what is an interval I can place around 4 so that when I map it through the function, all my outputs are within 2 units of 7.
Okay. And you just pick 2 as whatever.
2 is just whatever so far.
So it can be any number. That's
Right. We're going to pick smaller and smaller numbers for 2 just to get you started with the game.
okay.
Okay, so f of x minus 7, we know that we want that to be less than 2. What is f of x?
2x minus 1.
2x minus 1. So we want 2x minus 1 minus 7 to be less than 2. 2x minus 1 minus 7 is what?
2x minus 8.
2x minus 8 to be less than 2.
Divide by 2.
Divide everything by 2. And we get x minus 4 is less than 1.
Yeah.
So notice that if the distance between x and 4 is less than 1, then the distance between f of x and 7 is less than 2.
The distance between x and 4 is 1.
Less than 1.
Okay.
Then the distance between f of x and 7 is less than 2.
That's pretty cool.
And that tells us what you showed right there.
And that tells you exactly what, just looking at the picture, you could have guessed.
Yeah.
How far to the left here could I have gone and still mapped into this interval? I could have gone all the way to 3. Plug 3 into the function, it comes out 5. Plug 5 into the function, it comes out 9. Anything between 3 and 5 down here gives you between 5 and 9 up here.
Okay.
Right?
Yeah.
Now, we don't have to be that restrictive. We just found the smallest, we found the biggest interval here. It's also the case if I would have said f of x minus 4, if I would have said the distance is less than 1/2. If we looked at all the points within 1/2 of 4, then it would also have been the case that all their points map to in this distance. So when we write out this algebra, this being true implies this is true, implies this is true, implies this is true, implies this is true. So if my distance from x, if the distance x is from 4 is less than 1/2, then the distance x is from 4 is less than 1.
Yeah.
And so then the distance 2x is from 8 is less than 2. Or 2x minus 1 minus 7, its absolute value is less than 2. Or f of x minus 7 is less than 2. So if this is true, then this is true, then this is true, then this is true, then this is true.
Yeah.
So if you pick a point that satisfies this, then the image of that, you guys okay with the image of a point? Or is that terminology you're not used to?
I've never heard that.
You never heard that? The image is just the output. This is the image of x.
So it's
The y point.
Okay.
So if your x is within 4, or is within 1/2 of 4, then your y is within 2 of 7.
Yeah.
So if this is true, then this is true.
So the output is not determined by the number you put in, okay, I think I got it.
So let's play the game again. This time, I want you to find all the points that are within, this time we'll say 0.02 of 7. So now this time we only want to go up this. I want you within this little interval right here of 7. Much smaller than what I drew, but I don't want to draw that.
Determine it on the bottom first and then the top.
We need to find an interval you place around 4. So that when you run it through the function, it falls in this teeny interval around 7.
Oh, okay.
So that's the name of the game. You're always looking for the bottom interval
Yeah, always.
that fits into the top interval. You're always looking for a way to bound x so that y is bounded the way you want.
Right. Okay, so first step is to substitute your f of x, right?
So once again, so f of x. So ultimately we're trying to say x minus 4, what do we have to bound that by so that f of x minus 7 is bounded by 0.02? So we're ultimately looking for a number to put here. What number can I put here that makes this true?
0.01.
0.01, it turns out, is going to work. Good intuition. I want to take you through the algebra and see the algebraic steps.
Isn't it the same thing as
It's going to be the same thing.
Makes sense.
So just see the thinking one step at a time, and then that way when we do this in proofs, hopefully, when it's just variables, it doesn't confuse you.
Yeah.
So, once again, what is this? What's f of x?
2x.
That's 2x minus 1, and we still have a minus 7. That absolute value, we want that less than this.
Yeah.
Simplify, that's 2x minus 8. That absolute value less than 0.02. Right?
Divide by 2.
Divide by 2, and that gives us that x minus 4 absolute value is less than 0.01. And so we found it. If this is true, then this is true, then this is true, then this is true.
Yes.
Yeah.
So we found some interval you can place around 4 such that its the y's are in this interval around 7.
Could you derive it backwards? So go x minus 4.
Well, this is the way that you're always going to be looking for it. When we go over the definition, it will make more sense why we're deriving it this way. But the point is now, I don't give you this number. I'm not going to give you an arbitrary number. I'm going to say, I want you to find some number here such that when I run it through my function, it is less than epsilon. What's epsilon? Some positive number.
Epsilon.
Yep.
Okay.
Could be 0.00001. The point is, we're going to come up with a procedure. So that no matter what number I give you for epsilon, you can always find me a corresponding number down here.
Which is delta.
That makes it true, which we call delta. So, I want f of x minus 7 is less than epsilon. Well, then that's when this is less than epsilon. That's when this is less than epsilon. And that's when this is less than,
Epsilon down.
nope. That's when this is less than epsilon over 2.
Yeah.
So then I'm going to write right here, let delta equal epsilon over 2. And then, if x minus 4 is less than delta, then x minus 4 absolute value is less than epsilon over 2. Multiply by 2, then this is true, then this is true, then this is true. You see how if this is true, then ultimately this top thing is true.
So you'll always have an epsilon with a delta.
You're going to be given an epsilon, and your job is going to be find the delta.
Okay.
And your delta is going to have to be expressed in terms of epsilon.
Right. Okay.
Because for a particular epsilon, you need a particular delta.
Okay.
Make sense?
Yeah.
That's going to be the name of the game. What are we going to say is the limit of a function at a point?
In between those intervals.
Well, now we're going to define what we mean by the limit of a function at a point. So far, we've just been saying what it gets really, really close to. So as you take really, really small epsilons around 7, then you're going to be taking really, really small deltas around 4.
Yeah, and that's just intuition, right?
Well, now I'm going to read you the precise definition.
Okay.
So here's the precise definition now. Let f of x be defined on some open interval around the point C, except possibly at C. We don't care if the function is defined right at 4. We could have had a hole right here. That doesn't change anything. Maybe the function wasn't defined there, but it's defined everywhere else around 4.
Yeah.
Okay. We say that the limit of f of x as x approaches C, some number C, in our concrete case here we were using C as 4. We say that the limit of f of x as x approaches C is L. In our case, L was
Epsilon.
7. It's what our function was
so it's L,
approaching.
that's right.
That's our L.
Okay.
So f of x, let's just say it one more time. We say that the limit of f of x as x approaches C is L, and we write that the limit as x approaches C of f of x is L, provided that for every positive number epsilon out there, there exists some positive number delta, such that for all x, if the distance between x and C is less than delta, then the distance between f of x and L is less than epsilon.
Is that the actual definition? Not
Yeah.
notion?
This is the precise definition.
Okay. Well, I'm just saying that notion right there specifically.
The full-blown definition, there it is.
Alright.
Not hiding anything from you. So, in showing that the limit of f of x at C is L, you need to show that this implication holds. You need to show that if the distance between x and c is less than delta, then the distance between f of x and L is less than epsilon, which is what we did. X, c, delta, f of x, L, epsilon. Now, you might notice on the left-hand side we have, oh, and this thing's greater than 0.
Yeah, 0.
Why is this thing greater than 0?
Because if it's 0, then...
We never let x actually be c. We never use the point c itself. We just use points arbitrarily close to c.
So why can't it be -1?
X could be potentially -1, but
Oh.
x can't be c, the point that we're talking about.
It's the absolute value.
Because there could be a hole there. I can't plug 4 into this function if it has a hole right at 4.
Yeah.
But it can still have a limit there.
Right.
So the limit doesn't care what's going on at the point C. It only cares what's going on around the point C. And so that's why there's this greater than 0 piece to it.
Yeah.
But in the limit, we never let x equal c, so it's
It's just
not uncommon to kind of ignore that piece and just write it without it. It's just kind of understood. Bit lazy, but understood. So now, if you want it all in one go with the more dense notation, rather than reading that whole thing, here it is. The limit as x approaches c of f of x equals L, we define that to mean for every epsilon, there exists a delta such that if the distance between x and c is less than delta, then the distance between f of x and L is less than epsilon. There's how it says if you're like that dense notation.
Is there a difference between implies and equals?
Yes, implies and equals are very different things.
Yeah.
Implies is what?
You're wearing shoes implies you're wearing socks. Shoes and socks are not equal to each other.
Oh, okay.
So implication says if this is true, then this is true. Over here, this implies this. If we knew this, then we knew this.
Yeah.
These are not equal to each other.
Yeah.
It's just that this being true implies this is true.
Okay.
Okay. So there's the name of the game. There's our definition. Let's think about explaining continuity, and we'll just put that to next week. We need to dip into it right now just because they're so closely related, but I changed my mind. So ignore that picture. Okay, so the limit of a function equals L, provided that no matter how small your epsilon is, so here's how this epsilon is our max distance away from L. Pictorially picturing all this, here's where it is. If this is L, then the top of our boundary here is going to be L plus epsilon. That's the max distance above L you can go, if epsilon is the range that we're staying in.
Yeah.
And L minus epsilon is as far down as you can go, if we're staying within epsilon of L.
And L is the limit.
L is going to be the limit of this function f
At C.
at this point C. And so, our delta is how much we move away from C. So our interval goes from C plus delta to C minus delta. So we're mapping this interval up into that interval. Now remember that this interval doesn't have to take up the whole interval, it just has to map into it. So there's an infinite number of deltas that would work once you get your epsilon. For this epsilon, this delta works. I could have also used half that, or half that, or half that, or half that, or half that. So there isn't the right delta. There's just a delta. That's all you're after. Okay. And so that's what it means when we say the limit of this function at this point. Since it has to be true for any epsilon, then as epsilons get arbitrarily small, there still has to always be some delta around C such that it maps into there. Make sense?
Yeah.
Okay, let's do some proofs using this. Probably should have left that for a second. I don't know if we'll need scratch work. I'll leave the algebra that we have right there in case that's useful. Okay, so let's play the game again. Here's what we've got. Here's our new function, f of x. We're going to prove that the limit as x approaches 1 of 5x minus 3 equals 2. Right? So I'm just going to call 5x minus 3 f of x. And we're going to let epsilon be some positive number greater than 0. We have no clue what this number is. Our job is to find the delta. So we know that we want f of x minus, what's our L going to be?
-3.
Our L?
No, it's your function.
It's what it's approaching. It's what our limit equals.
Oh.
Our L is what it equals.
Yeah, but what did you plug into the 2?
We're proving that the limit as x approaches 1 of this thing is 2. We're going to prove
yeah,
it.
that's right.
So our L here is 2. So f of x minus L, we want this to be less than epsilon, right?
Yes.
We are looking for the delta such that x minus c, what's the point that we're approaching?
2.
1.
Yeah.
1.
1. X minus c. Remember, c is what you're approaching down here.
That's what x is equal to.
It's what x is approaching. The distance between x and c is less than delta. We need to find the delta that goes here, such that if this is true, then this is true.
Oh, yeah.
So I gave you some arbitrary epsilon. Your job now is to find the delta.
Yes.
How do you do this? Exactly like what we did before. What is f of x?
5x
5x minus 3.
5x minus 3, and then we minus 2. And we want that to be less than epsilon. Right?
Then we don't necessarily need to classify what epsilon is.
Epsilon is some random number that I gave you.
Okay. Well,
It's 0.000176459.
yeah,
There it is.
Oh, okay, yeah, I see.
Okay? So that's the number epsilon. Okay, so we want this distance, or we want this absolute value to be less than epsilon. Simplify 5x minus 5. We want that to be less than epsilon.
Now you divide.
Factor the 5 out, or if you can see it all in one go, divide everything by 5. That will happen when x minus 5 is less than epsilon fifths. Sorry, x minus 1.
Yeah.
We divide everything by 5.
Yeah.
So what does x minus 1 have to be less than in order for f of x minus 2 to be less than epsilon?
Delta over 5.
X minus 1 has to be less than epsilon over 5. Right?
Yeah, but delta equals that.
So we say let delta equal epsilon over 5. And then, if x minus 1 is less than delta, this is true, this is true, this is true, this is true.
Correct.
So it's standard when you're doing these proofs that you do some scratch work to the side to figure out what you want your delta to be.
Why do you mean that?
Well, now here's the actual proof.
Okay.
So I did the scratch work, now I'm writing out an actual proof.
Okay.
Okay. So observe that f of x minus 2 is equal to 5x minus 5 is equal to 5 times the absolute value of x minus 1.
Right.
Right? Similar thinking to what we did over there. We just didn't factor out the 5 first and then divide by it.
Yeah.
And then, no. And then at this point I can see, okay, what's the delta I'm going to want? It's going to be epsilon over 5.
Okay.
So then, if x minus 1 is less than delta, what does that mean? If the absolute value of x minus 1 is less than delta,
Then that means.
the absolute value of f of x minus 2, which is the same thing as this, that's what we showed up here.
Yeah.
The absolute value of f of x minus 2, which is the same thing as this, is going to be less than 5 times delta. Why? Because this thing is for sure less than delta. The absolute value of x minus 1 is less than delta. Right?
Yeah.
The absolute value of x minus 1 is less than delta. And so 5 times the absolute value of x minus 1 has to be less than 5 times delta.
Yes.
Yeah.
What is 5 times delta?
It's epsilon.
It's epsilon.
Yeah.
So I showed that if x minus 1 is less than delta, then f of x minus 2 is less than epsilon.
Well, now it's your definition of. Yep.
So therefore, x minus 1 being less than delta and greater than 0, but that distance being less than delta implies that distance is less than epsilon. So I just barely proved that the limit as x approaches 1 of this function is 2. I just barely showed that for any epsilon you choose around 2, I can find a sufficiently small delta around 1, such that if x is within delta of 1, then f of x is within epsilon of 2.
Oh, okay.
Okay.
Let's do another concrete one.
Okay, that actually makes sense.
So here's one of the limit laws that we had last time. We said that the limit as x approaches c of x is just c.
Right.
Let's actually prove that now, rather than just stating it.
Okay.
So, let f of x be x. That's the function we're talking about. It's just the identity function.
Yeah.
Straight line, 45-degree angle.
Yep.
So let f of x equal that, and let epsilon greater than 0 be given.
What do you mean by be given? Is that just, you're just assuming that?
Let epsilon be any positive real number.
Oh,
Just an arbitrary positive real number. We don't know what it is.
alright.
Okay. Now, what are we looking for?
Proving limit.
We want to find, let's see big picture what we want. We want if x minus, what's our c? C is less than delta, we want that to imply that f of x minus L is less than epsilon. So we want to find the delta that makes this true, right?
Yes.
Yeah.
Okay. So, what is the absolute value of f of x minus, oh, what's our L? Sorry, what's our L in this case?
L is L. L is C.
C.
Okay.
Just
L is what we're claiming the limit is.
Yeah.
C, in our equation there, is what x is approaching.
And we're trying to prove that.
So we're trying to find the delta, such that when this is true, this is true.
Yes.
Now what is the absolute value of f of x minus c equal to?
It's x minus c.
X minus C.
It's equal to the absolute value of x minus c. What delta do I need so that f of x minus c is less than epsilon?
Yeah,
Yeah,
it's
Epsilon. Perfect. 3. Let delta equal epsilon. 4. Then, if x minus c is less than delta, that implies that, I don't think I need to write this one out much, f of x minus c is less than epsilon. We just wrote the same thing twice.
Yeah.
So in that case, there it is. What's the delta you use? Whatever the epsilon is.
Okay.
And that is showing that on any point that you're approaching, you can find intervals around.
Pick any point c you want on this function, and you say, how much you have to bound the inputs by to make sure that your outputs are bound by 1/100? The answer, 1/100.
And you can just get increasingly small intervals until you have the limit. at that
Well,
point.
you can pick a smaller epsilon. That gives me a smaller delta. That works. You pick an even smaller epsilon. I got an even smaller delta. That works.
Well,
For
it's-
any epsilon you choose, I can always find a sufficiently small delta. Now, we didn't have to say delta equals epsilon here. We could have said let delta equal epsilon halves. And it still works.
Right.
Because if x minus c is less than epsilon halves, x minus c is for sure less than epsilon.
Yes.
So there's infinitely numbered deltas that work.
Right.
It's just delta equal to epsilon somehow feels like the most natural delta. Okay.
What happens if we don't know where the limit is?
Sorry, what?
We knew we were trying. In that case, we were trying to prove that the limit of that was c. But what do we do when we don't know what the limit is? How do we find the limit?
Oh, how do you evaluate a function for its limit?
Yeah.
Typically, you can see what you think it's going to be. This isn't a procedure for making a calculation. It's a procedure for proving this particular point. I mean, you'll learn techniques for calculating limits as the book goes on.
Okay.
All right, let's try another one that we've already done before. We want to prove that the limit as x approaches c of just a constant function,
Is
so this is just y equals k, it's just a horizontal line. Prove that the limit as x approaches c of k is equal to k.
Okay.
Yeah. So let f of x equal k, and let epsilon greater than 0 be given. Any positive number. Observe that. What is the absolute value of f of x, let's see, minus, what's our L? What are we approaching?
Okay.
K.
Well,
What's that equal to?
Aren't we approaching C?
No, we're talking about.
Oh.
X is approaching C,
not
our
limit.
L is K.
Right.
Our outputs are approaching K. Our inputs are approaching C. Okay, so f of x minus K. What is f of x?
Okay.
K minus K is equal to 0. And we want that to be less than epsilon. What delta do I have to bound x by? So I need x minus c is less than some number. What number do I have to put here to make sure that k minus k is less than a positive number?
A negative number.
When is k minus k less than a positive number?
Anytime you do it.
Always! It doesn't matter what our delta is in this case.
Yeah. Oh.
So in other words, 3 let delta equal 10 million.
Okay.
4. Then, if x is within 10 million of c, that implies that f of x minus k is less than epsilon.
Yeah.
Doesn't matter where our delta is. Intuitively, hopefully you can see that with a constant function. Here's our constant function at height k. Pick some point C. What interval do I need around C? And pick any small interval around k you want. What interval around C can I use to make sure that when I map it, all the outputs are inside that interval?
Anyone.
In an interval I want. If I use this big of an interval, let's see, that maps to there, that goes inside. That maps to there, that went inside.
Yeah.
Doesn't matter how big of an interval I use, when I map it, it all fits within that small interval around k.
Okay.
Yeah, makes total sense.
So that's intuitively what that proof is screaming at us. Okay. So now let's do a couple more. I'm not going to write them out completely formally now. I'm just going to walk you through the algebra part of coming up with the delta. Okay?
Yeah.
Maybe we can leave this. Remind us what we're always looking for. For any epsilon, we're looking for the delta that makes this implication true. All right?
Yeah.
So our next problem, the author says, it's given that the limit as x approaches 5 of this thing is equal to 2. So we're not proving that that's given to us. He says, find a delta for when epsilon is equal to 1. In other words, find a small enough interval so that when you map it through the function, it is always within 1 of 2. So this is similar to what we were doing at the very beginning.
Oh.
So in other words, we want the distance between f of x and our limit. What's our limit? 2.
Oh, when.
Yeah, we evaluate the limit of this thing is 2.
Okay.
So we want the distance between our output and 2 to be less than what?
1.
1, our epsilon here. So we are looking for x minus, what's our c in this case?
1. Wait.
C is.
Oh, it's 5.
5.
It's 5.
We're saying, how close do we have to keep x to 5 in order to make sure that f of x is within 1 of 2?
Yep.
Right? So we're looking for the delta that we plug in right there. Okay. So f of x minus 2 is less than 1. Let's plug in our f of x. What's f of x? Square root of x minus 1 minus 2. And we want that to be less than 1. Not going to do this derivation for you, but you might remember from your algebra that if the absolute value of a is less than b, that is the same thing as negative b is less than a is less than b.
Yeah.
So, same thinking here. This means that this thing, negative 1 is less than the square root of x minus 1 minus 2 is less than 1. Whatever this thing evaluates to, it can't be more negative than negative 1. Otherwise, when you take its absolute value, you get something bigger than 1. And when you evaluate this thing, it can't be more positive than positive 1. Otherwise, when you take its absolute value, you get something bigger than 1.
Right.
Okay, so now add 2 to all 3 sides.
It can't evaluate to 1 either, can it? Because it's less than 1. So it's not less than or equal to 1, so it can't evaluate to be 1.
True, it can't evaluate to be 1. And so we still haven't allowed that.
Yeah.
I'm just trying to make your intuition quick as to how this and this are saying the same thing without the right hand.
Okay.
Okay, now plus 2 to everything. If this is less than this is less than this, then if I add 2 to all of them, the inequality should still hold.
Right.
Yeah.
If I'm poorer than you is poorer than John, and someone gives all of us $2, the order still holds.
Right.
So, that gives us that 1 is less than x minus 1 is less than 3.
Mhm.
Okay? Now, if these are true, squaring everything doesn't change it. If this number is less than this number is less than this number, since they're all positive, this number squared is less than this number squared is less than this number squared. Only works when they're all positive. Why does it only work when they're all positive? Look at -3 is less than 1.
Okay.
That's true. Now square them both, and you get 9 is less than 1. No, it doesn't work.
But they all can be negative or positive.
These are all positive numbers. Because that's 1, that's greater than 1,
Yeah.
and that's a positive number.
But if they are all negative, you can still do it too.
If they were all negative, then you could do it, but you flip all your inequalities.
Right.
So I know that -5 is less than -3, square everything, that gives me that 25 is greater than 9. Okay, but anyway, since they're all positive, we don't have to think too much about it. Okay, square everything, and what do we get?
1 is less than x minus 1 is less than 9.
1 is less than x minus 1 is less than
9.
9. Now what were we trying to bound? We're trying to bound x minus 5.
Yes.
I need to find out what x minus 5 has to be less than to make this true. You with me?
Yeah.
Okay, so I need -5 to show up somehow. So I'm just going to subtract 4 from everything. Just forcing my 5 to show up. So here we would get -3 is less than x minus 5 is less than,
5.
just subtracting 4 from everything. You with me? Okay, now remember which way our logic is going to flow here. We're saying that if this is true, then this is true. 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 Right?
Yeah.
That's the order of our logic. And so if x minus 5, let me just write the step in this in. -3 less than x minus 5 less than 3. If x minus 5 is between -3 and 3, then x minus 5 is for sure between -3 and 5. So it's still the case that if this is true, then this is true, then this is true, then this is true, da da da.
Right.
Our chain of implications work. Remember, the implication, we only care about going this way.
Yeah.
We don't care that this doesn't imply this. We just care that this implies this.
That's difficult for you to show.
Oh, isn't it?
Let me try it another way. I could replace that with -1 and 1. Still works. If this is true, then this is true.
Yeah.
So why wouldn't you subtract 3 to originally? Oh, actually. No.
Well, now I'm just going to rewrite this as the absolute value of x minus 5 is less than 1. What did I just really say? I said that if x is within 1 of 5, then the output of x is within 1 of 2. And you can try that. Pick a number that's within 1 of 5 and plug it into your function. Our function was this thing, or was this thing. And you're going to get a number that is within 1 of 2. This being true implies this is true, right?
Yeah.
Which implies this is true. Which implies this, which implies this, which implies this, which implies this, which implies this. So if this is true, then this is true. If x is within 1 of 5, then f of x is within 1 of 2.
But how do we know?
Now we didn't have to do 1s here. We could have done 3 and 3. That still works. If this is true, this is true. So then that makes this 3. And it still works. If x is within 3 of 5, then f of x is going to be within 1 of 2.
Yep.
Let's just think. What's a number within 3 of 5?
3 and
Well, 2's just outside.
4.
So we can use 4 if we wanted. So let's try 4. So plug 4 into our function. Where was our function right? It's right here. What's 4 minus 1?
3.
What's the square root of 3? 1.7 something.
Yeah.
Is 1.7 something within 1 of 2?
Yes.
Yes. It worked. Pick something else in this interval.
7.
7. What's 7 minus 1?
6.
6. Square root of 6, what is that? 2 point something. You don't get to 3 until you get to the square root of 9.
Right.
So the square root of 8, 7, 6, those are all going to be less than 3, but more than 2. The square root of 4 gives you 2. The square root of 9 gives you 3. So the square root of anything between 4 and 9 gives you 2 point something. Right? So we found a delta, namely 3. We could have also used 1. We could have also used 1/2.
Oh, okay.
Yeah.
Remember which way your implications go. You're used to, in a derivation, thinking this implies this implies this implies this implies this. That's not what you're doing. You're constructing lines so that the bottom line implies the top.
That's so weird.
Now, for the most part, they're just logically equivalent. And it's only when you get stuck that you're like, oh yeah, I have to use a little trick here. And remember which way the logic goes. So the only really weird step is going from here to here. But it's okay because we're just being more restrictive on our inputs.
Why do we have to do that? Why do we have to make
I just needed to somehow get absolute value of x minus 5 is less than something. I see he keep manipulating this until I can get absolute value of x minus 5 less than something.
Less than positive.
Less than a positive number, yeah, because absolute value is positive.
Right.
And so it can never be less than a negative number. So I need to bound x minus 5, the absolute value, by something. And so that's why I want the same number on both sides, because I know how to make an absolute value pop out.
Yeah.
If I would have switched this to negative 5 instead, then we would have broken it. Because this no longer implies this. We could not have written it like this. Negative 5 and 5. Because this no longer implies this. If I know that x minus 5 is between negative 5 and 5, I do not know it's between negative 3 and 5.
Oh, you have to restrict it more. You can't make it a bigger number.
You can always restrict it more. You can't expand your interval. Because if a bigger interval worked, so would a smaller.
Yeah.
Right.
So you can always shrink the interval you're talking about. You can't ever expand it. That's dangerous.
So
It might accidentally be the case that this happens to work, but that would be an accident.
you're not trying to derive the delta, you're just trying to find one.
Yeah, there isn't the delta. There's a delta.
There's many deltas.
There's an infinite number of deltas. Which is one of the things that makes these seem weird. There isn't the right answer.
Yeah.
Well, these,
There's just right answers.
Yeah.
Make sense?
yeah.
Okay. Let's try another one. Maybe this one will write out the full proof again. I don't know if it helps more when we write out the full proof. It doesn't make no difference.
Algebra works fine for me.
The algebra works fine?
Mm-hmm.
Alright, so let's look at this one. We're trying to prove that the limit as x approaches 2 of f of x is equal to 4,
Okay.
where f of x is equal to this piecewise function.
Okay.
It spits out x squared when x isn't 2, and it spits out 1 when x is 2. Maybe just quickly scribble a picture of this thing to help our intuition. I'm not going to draw it too good. But what is it essentially? It's a parabola with a hole right there that comes back up.
The whole where x is 2.
Yeah.
Oh, thank you.
Yeah.
Right. So over here where x is 2 and it goes up to 4, there is a little hole, and instead the function is spitting out a 1.
Okay.
So there's our picture, and we already know just from looking at the picture, what's the limit as x approaches 2?
4.
It's 4. We don't care about that hole when we're talking about limits.
Yeah.
So we already know that should be the case. Let's prove that it is the case.
Okay.
Make sense? Okay. So we want our f of x minus, what's our L going to be?
4.
maybe write out the whole implication that we're after. Let me just rewrite this implication for our concrete case. So we want if x minus what? 2 is less than delta. We're looking for the delta that makes this true. Then f of x minus what? 4 is going to be less than epsilon. We're looking for the delta that makes that true for any epsilon.
Why do you have C written up there?
That should be L, shouldn't it?
On the second one.
Okay, that should count.
Because when we wrote this, it was particularly for the case of the identity function.
Yeah.
Oh.
And it wasn't written in general. Thank you. Okay. Anything stupid I have written up here, or does it all make sense?
That makes sense.
So far, it makes sense.
Yeah.
Okay, so now let's start looking at f of x minus 4. We're going to start evaluating that and see what this would have to be bound by to keep this less than epsilon. So epsilon is some secret number. For all we know, it's something like 0.00127. Think about epsilon as being that number if it helps your intuition. So we want to find out what delta has to be to make sure that this distance is less than that.
Yes.
Okay. So what is the absolute value of f of x minus 4 equal to?
How do you put piecewise function in there?
How do you put piecewise function in there? What are we approaching?
You're approaching 4. Or you mean
2.
We're approaching 2. So what is the one number I'm never going to plug in for x? 2. So we don't care how this behaves at 2.
Oh.
So f of x minus 4 is equal to x squared minus 4.
Feels like cheating.
Well, I'll write the qualification at the end of the line. Is equal to the square root of x minus 2, x plus 2. Right? Difference of squares.
Yes.
Is equal to the absolute value of a product is the product of the absolute values. So the absolute value of x minus 2 times the absolute value of x plus 2, comma, where x is not equal to 2.
What if you have a piecewise function that has multiple holes in a function, and you're trying to find the limit at one point? How would you incorporate that?
All it matters is you can find an interval containing the point.
So you can ignore
Let f of x be defined on an open interval around the point. And it doesn't matter which open interval you use. So you don't have to use a whole domain. So get a small enough open interval that gets rid of all the bad points you're talking about and work from there.
Okay. Makes sense.
Okay.
Good to know.
Okay, so we've got that, right?
Yeah.
We're ultimately trying to figure out what x minus, what's our c? 2. We want to see what that has to be less than to make all of this true. So we've already got our x minus 2, right?
Yeah.
But the problem is we have this x plus 2.
Right.
Yes.
So how are we going to move forward with it? We somehow need to bound that x plus 2 by something. Now, if I find a delta that works, and I pick a smaller delta, my smaller delta will always work for sure,
Yes.
right?
Yeah.
So I am going to say, let delta equal the minimum of 1 and then something we've yet to discover, what we would have typically called our delta. But if I know that I'm not going to let my delta be bigger than 1,
Where'd you get 1?
I picked a number out of the hat. You can pick any number here that you want. Once I pick a number that delta can't be bigger than, that is going to bound what x plus 2 can't be bigger than.
Then how do you know that's less than epsilon?
How will I know that's less than epsilon? This other thing is going to make it less than epsilon. 1 only comes into effect if this thing happens to be bigger than 1. If it happens to be smaller than 1, the fact that I bounded it by 1 doesn't matter. If it happens to be bigger than 1, well then 1 also works. So making delta the minimum of two numbers, so before we would have said delta is equal to some expression that has epsilon in it, right? Some expression using epsilon. That's what we would have had.
Yeah.
Now we're going to have delta is equal to the minimum of 1 and some expression using epsilon.
Why, what's the point of that?
So
Because
if I know that delta can't be bigger than 1, and I know that, so here's, maybe this would work better if I wrote it as a proof. So I'll just say 1, observe this, that, 2. Let delta equal the minimum of 1 and something I'm going to come back and plug in later when I'm done. I don't know yet.
Okay.
So what am I trying to show, big picture in my proof? I'm trying to show that if this is the case, then this is the case.
Yeah.
So now, assume x minus 2 is less than delta. Whatever that delta is, x minus 2 is less than delta. And we want to show that this implies this. F of x minus 4 is less than epsilon. Right? So that's what remains to be shown.
Right.
Now, since, and here's the magic of it, x minus 2 is less than delta, I know for sure that the absolute value of x minus 2 is less than 1. How do I know that? Because whatever my delta is, it's at least going to be, the most it could possibly be is 1.
Yeah.
Right? So if this thing's less than delta, it has to be less than 1.
Okay.
That make sense to everyone? So if x minus 2 absolute value is less than 1, what does that give me? That gives me negative 1 is less than x minus 2 is less than 1. Which gives, sorry, that was an arrow. That gives me this,
Yeah.
which gives me plus 1 to both sides, or plus 2 to both sides. That gives me 1 is less than x is less than 3.
Yes.
So for sure, my x has to be between 1 and 3.
So there's your.
Which means you're, yeah.
So 5. So then, what does x plus 2 have to be bounded by? What is this for sure less than? If the biggest x can possibly be is 3.
Let's be,
3.
If the biggest x can be is 3, what's the biggest x plus 2 can be? 5. Okay.
my bad.
Okay, so now we say, here's where we tie it all together. 6. Then, and now I can come up here and I can plug it in, and I know that my magic number here now is going to be epsilon fifths. Maybe you can't see that yet, maybe you see it. If not, let's write through the logic now. So I know that x minus 2 is less than delta, and delta is whatever's smaller out of these two things. Right?
Yeah.
So x minus 2 is for sure less than 1, and x minus 2 is for sure less than epsilon fifths.
Yeah.
Yeah.
Because it's smaller than whatever's the smallest out of those two things.
Yeah.
Okay, so then, let's look at f of x minus 4 now and see what's less than. And see that it is less than epsilon. So f of x minus 4 then, that is equal to, jumping to over here, that's equal to the absolute value of x minus 2 times the absolute value of x plus 2. With me so far?
Yes.
X plus 2 cannot be bigger than 5. So this is going to be less than the absolute value of x minus 2 times 5.
Yeah.
Yes. Yes.
The absolute value of x minus 2 can't be bigger than delta. So it can't be bigger than epsilon fifths, and it can't be bigger than 1. So it for sure can't be bigger than epsilon fifths. So this is less than epsilon fifths times 5, which is equal to epsilon. And that's what we were after. I showed you that if x minus 2 is less than delta, then f of x minus 4 is less than epsilon. We did the minimum of two things, common trick. when you have two variable expressions that you need to get rid of. I like that I have the x minus 2. I know that ultimately I'm going to make that less than delta when I'm doing this problem. So I'm not worried there. What I was stuck by is what to do with this piece. So I just need to bound it by some constant number. Doesn't matter which.
Just so you can solve for it here.
So that I can find a number for sure bigger than this sinc to get rid of the variable. I need to find some upper bound for this number. There is no upper bound for this number until I create some upper bound on my inputs. So if I know that my inputs have to be within 1 of 2, then that gives me an upper bound on what this can be, which is 5. And now I can work with it the way we know and love.
Strange.
That is a lot to take in. These types of problems are the hardest problems you come across in calculus class.
Seriously.
And you get introduced to them early on. This is the hardest definition you will see in this class. These are the hardest types of problems that you'll have to work with and grapple with. It's all downhill from here. You're at the hard part, and it comes early.
Oh, integrals were the hard part.
The definition of an integral and using Riemann sums can be hard, but you don't do that except for in real analysis. So in real analysis, the limits is not the hard part.
Isn't solving for integrals hard then?
No. You learn operations for solving integrals the same way that you learn operations for working with algebraic expressions. So there'll be basic rules for working with integrals, and they're not that difficult. So this is the hard stuff. And I told you that this is the definition of calculus. This will be what you struggle with. Being able to calculate limits, that's what you will struggle with. Being able to solve a derivative, that'll be trivial.
We didn't calculate limit here, we just proved that there was the limit. Or that the limit was 1.
No, we proved that the limit as x approaches 2 of f of x is 4.
Right, but we didn't solve to find the limit, did we?
Our proof tells us that the limit is 4.
Right.
The author, we're assuming that the author wouldn't have asked us to prove it unless it could have been proven. But solving it and proving it are one and the same thing. Go ahead, what were you saying?
No, man.
So what if we get a question where we don't have a given limit?
So he'll either ask you to find the limit of some expression, where it's just expected that you're going to use your intuition, like looking at this picture and just know.
Okay.
Or you would do something. So imagine he didn't say this. Imagine he said, find the limit as x approaches 2 of this function. What would we have done? He might have said, find the limit as x approaches 2 of this function and prove that your answer is correct. First thing we would have done is drawn up a picture and said, oh, well, it looks like it's 4. Now do the proof.
And that's basically solving it.
And doing the proof shows that 4 was the correct answer.
Oh, yeah.
If we tried to use an answer like 5, we would have gotten in trouble in our proof and we would have gotten stuck.
Yeah. Where would we have gotten stuck at?
So 5's kind of an ugly one for this problem, but let's imagine that we tried to prove that it was 9. 9 will come out okay. So then we would have got f of x minus 9 here, and then we would have gotten minus 9 here, and then we would have gotten minus 3, minus 3, minus 3, minus 3, or plus 3. And now we're really stuck with that. That's not even the thing I need. I need to somehow get an absolute value of x minus 2 to show up out of this thing.
But you're trying to prove that the limit is.
I'm trying to prove that the limit as x approaches 2 is 9, which is not. So I'm stuck, and I'm like, how do I go forward? And the reason I can't figure out how to go forward is because I'm trying to prove something impossible.
Why do you need an x minus 2 if you're trying to prove that limit is 9?
Because we're saying the limit as x approaches 2.
Oh, that's right.
So it's not an accident that the term we're looking for keeps popping up in these functions. That's a consequence of the fact that we're on the right track.
Is there? There's no way to get x minus 2 derived from that.
There could be ways to get x minus 2 derived from it, but then other problems will be popping up, and you'll be trying to get rid of problems. It's going to turn out it's impossible. to get x minus 2 by itself and something that we can somehow bound and have everything be okay. We'll run into problems no matter how we do it.
Yeah. Well,
So if you go to do it wrong, you'll end up in trouble. It just won't work. Because it will turn out that there are epsilons that break it. We'll be erasing this, so I don't know why I'm fixing it. Okay. Any other questions on that? We'll do one more proof.
Okay.
Alright. Let's do this last proof. Proving one of our limit rules. We're proving that the limit of a sum is equal to the sum of the limits. This was one of our limit rules that we introduced last time. I told you I'm just telling you it, we're not proving it. I gave you a whole list of limit rules.
Yeah.
This is the only one we're going to bother proving. Okay, so let's construct this proof. So one, I'm going to name the limits of these two things. So let the limit as x approaches c of f of x equal L, and the limit as x approaches c of g of x equal n. We're going to assume that both those limits exist. The author explicitly says it when he goes give it the proof, but I didn't write that up there. So we know that their limits exist, and we're just naming them L and M so far. What am I trying to prove? I'm trying to prove now that the limit as x approaches c of this thing is L plus M.
yes.
Because that's L and that's M. I'm trying to prove that the limit as x approaches c of this thing is equal to L plus M.
Yeah.
Okay. So I'm looking for, I need x minus c bound by some delta. We're looking for the delta so that what's our function in this case? It's f plus g.
F plus G.
So that f of x plus g of x, our function, maybe put parentheses to really help us see it, minus our limit is less than epsilon. Looking for the delta here. That makes this true. If this is true, then this is true.
Yeah.
Right? Okay, 2. So then the absolute value of f of x plus g of x, maybe put parentheses, minus our limit, L plus M, equals, we're going to need vertical space, shouldn't have written that there, or horizontal space, I mean. That is equal to, we don't need all those parentheses, so that's equal to f of x plus g of x minus L minus M. You see that?
Yeah. Wouldn't that
Just
be
distributing the negative sign term.
0? Wouldn't all that be 0?
No.
No.
F is a function. It's something like x squared.
Oh, that's right.
G is a function.
The limit of f of x now.
The limit of f of x as x approaches 2 is L.
Right.
Okay.
Okay, so now this is equal to, let's see if we have space right here. I'm going to do some grouping now. I'm going to group f of x with L. F of x minus L plus g of x minus n. You see my grouping there?
Doesn't change anything.
Doesn't change anything. Now, we're going to use something called the triangle inequality for absolute values. The triangle inequality is that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b.
Yeah.
Yeah.
Okay? So using the triangle inequality, then this is going to be less than or equal to the absolute value of the first thing plus the absolute value of the second thing. The absolute value of f of x minus L, point right parentheses, plus the absolute value of g of x minus n. Okay, so we've got that so far, right?
Yeah.
Yeah.
Oh, sorry, I forgot to get my epsilon. So let the limit of that equal that, and the limit of that equal that, comma. And let epsilon just be some positive real number. We have no clue what.
Yeah.
Okay, we need to find our delta. Now, I already know that the limit as x approaches c of f of x is L.
Yeah.
That's correct.
What does that mean? I already know that for any epsilon you choose, the absolute value of f of x minus L is less than, I know that for any value you choose, there has to exist oh yeah, that's L.
That's L.
And this is C. Why do I have a 2? So what does it mean that the limit as x approaches C of f of x equals L? It means that for any epsilon you choose here, there is a delta such that if this is true, this is true.
Yeah.
That's what it means. Pick any number you want here.
6.
So if you pick 6 here, I'm guaranteed that there's a delta that makes it true.
Yeah.
So 3. Since, write out explicitly, since the limit as x approaches C of f of x is equal to L, comma, then there must exist some delta sub 1, I'll call it, some delta sub 1, such that if x minus C is less than delta sub 1, that implies the absolute value of f of x minus L is less than any positive number I choose here. I'm going to choose epsilon halves. Let's wrap our head around the logic of that. I already know that the limit as f approaches C, as x approaches C of f is L. I already know that.
Yeah.
Which means for any positive number we choose, I chose epsilon halves. It's an arbitrary positive number.
Yeah.
For any positive number you choose, I'm guaranteed that there is some delta out there that makes this implication true.
Yeah.
Right.
Similarly, also since the limit as x approaches C of g of x is equal to m, I then know then there must exist some delta out there, I'll call it delta sub 2, such that if x minus C is less than delta sub 2, that implies g of x minus L is less than any positive number I choose. I'm going to choose
Less than
epsilon
M.
halves again.
Minus them.
Understand.
Thank you.
Oh, yeah.
And you with me?
Yeah.
Okay. 4. Let delta equal the minimum of delta 1 and delta 2.
Okay.
5.
Wait, what do those mean? The minimum of delta.
Of delta 1, this number, and delta 2, this number.
What's the point of saying that?
Delta 1 and delta 2, comma. And assume the absolute value of x minus C is less than delta. So remember ultimately what we're trying to show. We're trying to show that if x minus C is less than delta, then f of x plus g of x minus L plus m is less than epsilon.
Oh, yeah.
That's where we're trying to go. So, since x minus C is less than delta, is x minus C less than delta sub 2?
Yes.
And if x minus C is less than delta, is x minus C less than delta sub 1?
Yes.
Yes, because delta is whatever smaller of those two.
Yeah. Okay.
So if this was 1/2 and this was 1/4,
Yeah.
then x minus C is less than 1/4.
Oh, yeah, that's right. Okay.
And so is it true that x minus C is less than 1/2?
Yeah.
And is it true that it's less than 1/4?
Yes.
Make sense?
Yes.
So then, I know since x minus C is less than delta 1, this is true. And I know since x minus C is less than delta 2, this is true.
Yeah.
Because x minus C is less than delta, which is the smallest of those two. Overstating it?
No.
So then, the absolute value of f of x plus g of x minus our limit, which in this case is L plus m, is, we already know that this is less than or equal to, from our algebra up here, this is less than or equal to this plus this, is less than or equal to f of x first, is less than or equal to f of x minus L plus g of x minus m. But I know f of x minus L is less than what? Epsilon halves. And I know that g of x minus m is less than what? Epsilon halves. Which is equal to epsilon. And so I've shown that f plus g of x, f of x plus g of x, minus L plus m, is less than epsilon. So we showed that if x minus c was less than delta, then f of x plus g of x minus L plus m is less than epsilon. Therefore, as x approaches c, f of x plus g of x approaches L plus m.
How does epsilon plus or over 2 plus epsilon over 2 equal epsilon?
What's that? Wait.
Epsilon halves plus epsilon halves equals epsilon.
Oh yeah.
If you have half an epsilon plus half an epsilon, you have a whole epsilon. Right?
Well, what if it was like? Oh yeah.
Well, if it was a pizza. If you had half a pizza plus half a pizza, what do you have? A whole pizza.
Yeah. Okay.
Okay, any other questions?
Just a lot to go through.
It's a lot to take in.
Yeah, I'm gonna have to rewatch this.
Yeah. Go back and watch where we covered it in topology too, if that helps. Because we went over this exact definition in topology to show you how it was a special case.
It was easier to understand topology than this right now.
In topology, we had a lot of priming for it. Oh, is that going to fit? Yes. Okay. Fortunately, the next section is much easier.
When you say open interval, do you mean, is that the same notion of open interval as it is in topology?
Yep. Well, in the standard topology on the real numbers, every open interval is an open set. And really, what we care about is open sets.
Right. And we're working on a standard topology.
Yes, we just don't bother stating that.
Right.
Because the notion of a limit is much more general than what we have there.
Right.
That's the limit of a real valued function at a point.
Can't you define limits in terms of sequences?
Limits are defined in terms of sequences.
So what's that?
That is us jumping to talking about the limit of a function at a point.
Oh.
And so there's a sequential way that we could have come at all this. And it's a more natural way to do it. It just takes a lot of time to build up.
Like how we did it in topology? With,
Yes, in topology I gave you the actual definition of a limit.
with the big N. Okay, yeah. I see that. Here. Okay.
Okay. So one-sided limits. One-sided limits function just like limits. You're saying what is a function getting closer and closer to. But with one-sided limits, you either approach the point only from the right or only from the left. You don't just get arbitrarily close to it. You get arbitrarily close to it from a certain direction. So this section is now going to feel more like just talk about limits in a high-level way again, not so much the rigor. So 2.3, that's going to be your toughie. 2.4 will be easier again.
This is 2.4?
Yeah.
Okay.
One-side limit is 2.4. Okay, I think it's 2.4.
Yeah.
So we got some function here. This is a function, square root of 4 minus x squared. What is that function? You described it?
That's function. 2 minus x.
Isn't that 2 minus x?
Yeah, it's 2 minus x.
Pictorially, what does that look like? No? Okay, never mind.
Sorry.
Let me write this as,
Starts at
I think you'll see it here in a
2
second.
horizons.
Y equals 4 minus x squared. Right?
Oh, it's your...
Square both sides. Y squared equals 4 minus x squared. Move the x squared to the other side, and we get x squared plus y squared equals 4. Or 2 squared, if that just puts the nail in the coffin.
So it's a circle?
Circle!
What? How'd that work? That's
Almost.
weird.
It's only the top half of the circle. This is a circle. This is a circle. This, if you were reverse engineering, so here to here, you know how to take that step. This, if you take the square root of both sides, you have to write plus or minus.
And 2 is the limit of the
And so the positive gives you the top half of the circle. The negative gives you the bottom half of the circle. 2 is your radius, yeah. So it's the top half of the circle centered at the origin with radius 2.
Okay.
That's all this is. Right?
I did not see that at the first glance.
But you see it now for sure, right?
Yes, I'm sure I see that.
Okay, so just thinking about this pictorially, draw the top half of a circle. That's 2, that's 2, that's minus 2, right?
Yes.
Okay. First off, what's the domain of this function?
Any number but negative 2 and then 2.
That's wrong, so try again.
It's all numbers between negative 2 and 2.
Including negative 2 and 2.
Yeah, including.
Oh.
So the domain is negative 2 to 2,
Yes.
including the endpoints.
Right.
What happens if you plug 3 into there?
Doesn't work, it's outside.
You get a negative
Yeah,
number and a
negative
square root.
radical.
You get 4 minus 9 is negative 5. What's the square root of negative 5?
It's.
Bad question in this class. It's not a real number,
Right.
right? Okay, so these are the only numbers that you can plug into this function. You can take the square root of 0, that's fine. What's the square root of 0?
Sure.
See? Easy. Okay, so here's what the function looks like.
Yes.
Okay. Now, let's talk about some limits, just relying on intuition now. Let's look at the limit as x approaches 2, and you see I have that little plus sign after 2?
Yeah.
That means we're approaching it from the right.
Yeah.
Which is that way. Or that way.
Approaching from the right.
So going right to left.
Going right to left, approaching from the right.
Yep.
Using points to the right of 2. Okay, so question. What is the limit of this function as we approach 2 from the right?
2.
The height of the function, the limit of the function, the value of the function.
It's 0.
How tall is this function at 2? At 0, it's 2. Over here at 2, how high is it?
0.
0.
0. So as we get closer and closer to 2, what does the height of the function approach?
0.
It gets closer to 2.
It's 0.
It's
Our input is 2. What's our output? What's our height?
0.
0. As x gets close to 2, f of x gets close to,
0.
0.
if we plug in a number really, really close to 2 here, then when you square it, you get something really, really close to 4. 4 minus something really, really close to 4 is basically 0. The square root of something that is basically 0, basically 0.
Yeah.
Okay, say it again.
0.
As we approach x, as x approaches 2 from the right, what does our function get closer and closer to?
0.
0.
What's that?
0.
0.
Or
We're good.
how does it approach from the right of the?
How does it approach from the right? We can't go to the right of 2. There's no domain to the right of 2.
That's true.
So what is the right-hand limit of this thing? Undefined. Bad question. You can't approach it from the right. It's outside the domain.
Okay.
Right?
Does that mean if we try to take a regular limit, does that limit exist?
That's why we have this notion of right-hand and left-hand limits.
Is that
Maybe the idea of a limit doesn't make sense because we can't take some epsilon around 2 and run it through our function.
I see.
Because there are no points to the right of 2. So we can't use that definition.
That makes sense. Okay.
Right? Because any teeny tiny interval you put around 2 is going to get some numbers to the right of 2, which are out of our domain. So it doesn't have a right-hand limit. Now, what if we approach it from the left? What's the limit as we approach as x approaches 2 from the left?
0.
Now it's 0.
Right.
If we use points coming out from the left, as we get closer and closer, the value of our function gets closer and closer to 0.
Yep.
That one works just fine. All right. What is the limit as we approach -2 from the right?
0.
0. And what's the limit as we approach -2 from the left? Undefined. Bad question. You're somehow breaking it.
That makes sense.
Good?
Yeah.
Yes.
And that's the point of left-hand and right-hand limits.
Yep.
Well, one of the points. It enables us to talk about now, in some sense, intuitively, you already knew what you wanted to call the limit of that thing. So we just need some mathematical abstraction that captured that intuition you were getting at. Okay. Here's a theorem that we're not going to bother trying to prove. What does the theorem say? It says that if the limit as x approaches c of f of x is equal to L, then we know that the limit as x approaches c from the right is equal to the limit as x approaches c from the left is equal to L.
Right.
So one of the ways of trying to figure out the limit at a point is to see if a limit even exists. Take the left-hand limit, take the right-hand limit. If you get the same value, then that's the limit at the point. If you get two different values, there is no limit at the point. Give you intuition for a function that would instantly break this. Imagine I've got a function that comes along like this.
Right.
The left-hand limit is going to be this value. The right-hand limit is going to be this value. What is the limit at that point?
There is none.
There isn't one.
Yeah.
So there's a limit at a point if and only if there's a right-hand and a left-hand limit, and they give you the same value.
Yeah.
Similarly, if there's a right-hand and a left-hand limit that give you the same value, then that is the limit of the function at that point.
Correct.
Good?
Yes.
Okay, let's do some examples. Looking at this function, this weird looking thing,
Okay.
we're going to look at the limit as x approaches. I'm going to plug in 1, 2, 3, 4, and 5, and you're going to tell me the right-hand limit, the left-hand limit, and the total limit. So let's start with as x approaches 1 in each of these. What is the limit as x approaches 1 from the right?
Undefined.
One.
Well,
One.
It's just 1. As we approach 1 from the right, how high are we?
1. Oh, yeah.
As we approach 1 from the left, how high are we?
0.
0.
So what's the limit at the point?
Bad question.
Bad question. Doesn't have a limit at the point. Okay, let's look at it as we go to 2. What is the right-hand limit as we approach 2?
1.
1. What's the left-hand limit as we approach 2?
1.
1. What's the limit as we approach 2?
1.
But it has a hole there.
Real.
So on.
Who cares?
Yeah.
Right?
Right.
Alright. Repeat for 3. What's the right-hand limit as we approach 3? 2. What's the left-hand limit as we approach 3?
2.
What's the limit as we approach 3?
2.
Good. Let's do 4. What's the right-hand limit as we approach 4?
Undefined.
Bad question. Undefined.
Not really.
What's the left-hand limit as we approach 4? 1. And what's the limit as we approach 4?
Doesn't exist.
X.
I assume.
How is that first?
Undefined.
How is when you plugged in 1 for the first time that it was 2, and the other one it's not?
1.
What?
Is that point above 4 valid?
There's
Just
a-
below that.
Whole. That's the value of the function at 4. The value of the function at 4 is 1/2. But the right-hand limit,
Why
or the
can't-
left-hand limit as we approach 4 is 1.
Why can't you go right?
Because we're outside the domain. Same reason we couldn't go right with the circle.
That's right. That's right.
The function ends. It's only defined on this interval from 0 to 4.
Okay.
I guess we never did 0. So last point. What's the right-hand limit as we approach 0?
1.
1. What's the left-hand limit as we approach 0? Undefined. And what's the limit as we approach 0?
Also undefined.
Undefined. Make sense?
Yes.
Yeah.
Just intuition. Okay. What's the definition of a right-hand and a left-hand limit? So before in our definitions, we were saying that x minus c being less than delta implies f of x minus L is less than epsilon, right?
Yeah.
Now, x minus c less than delta, this piece can be rewritten as negative delta is less than x minus c is less than positive delta, right?
Yes.
Yes.
If we are approaching from the right, we never go,
To the left.
well, let me rewrite this one more time, plus c everywhere. So then we get c minus delta is less than x is less than c plus delta. Right?
Yeah.
If we are approaching c from the right, all our x's that we're using have to be greater than c.
That's true.
Look, c minus delta to c plus delta, that is going to be some open interval around c. C minus delta, c plus delta. Look at that open interval.
Yeah.
That's an open interval centered at c. Before, that's what we were using in our definition of a limit. If we're taking a one-sided limit, what are the points that we're going to use? If we're taking a right-handed limit, which points can we use?
C and everything plus C.
C and the points to the right of c. But we can't actually use the point c itself because we're taking a limit, right? So if our x's are going to be greater than c, the only difference is we get rid of that delta there. Here it is for a right-hand limit. We're saying all our x's have to be to the right of c within some delta. And if we were doing a left-hand limit, we would have rewritten it as c minus delta is less than x is less than c. And all our x's have to be, sorry, that's a less than c. Less than c. And all our x's have to be less than c now as we approach from the left.
Yes.
So this definition is identical to the one over there, except for, rather than saying x minus c has to be less than delta and greater than 0 to remind us that we never actually plug in c itself, rather than having our x's bound this way, our x is going to be bound this way for a right-hand limit, and this way for a left-hand limit.
Yeah.
That's the only difference. So now here's the definition. We say that f of x has a right-hand limit at a point c, and we write the limit as x approaches c with a plus there,
Yeah.
of f of x is L, provided that for every epsilon greater than 0, there exists a delta greater than 0, such that for all x, if x is greater than c and less than c plus delta, that implies f of x minus L, f of x is within epsilon of L. And for the left-hand limit, we would say that x being between c and c minus delta is less than f of x minus, or implies f of x minus L is less than epsilon. So it's identical definition, just replacing that first piece with a more restricted notion. Rather than this, it's either this or this.
Yep. Okay.
Because we're limiting ourselves to points to the right of c or to the left of c instead of some interval centered around c.
Yeah.
That make sense?
Yes.
Okay. So that's the precise definition of a limit. I don't think you'll ever have to use that precise definition,
Where would you?
but it may come up. In proving that the right-hand limit of something is a particular point, the same way that we had to use the definition of a limit in proving the limit of a point.
Yeah.
So I don't know that you'll ever have to work with that definition directly. You will have to work with that definition directly. But there's this precise definition.
Yeah.
But even if you have to work with it directly, we typically just work with that definition and then restrict our domain at the end to the domain that we wanted.
Yeah.
So give you an example of that. So I'm going to prove to you that the right-hand limit of the square root of x is equal to 0.
When you add your plus or minus, does that go behind your function or does that go on C?
It goes, it's like a exponent to your c,
Okay.
a superscript to your c. That's the proper way to say that. Okay?
Right.
So I'm going to prove that the limit as the right-hand limit as x approaches, or of the square root of x is 0. What does the square root of x, what does that function look like? It just looks like, just draw it really roughly, it looks like this. And there are no points to the left. So this can only have a right-hand limit at that point. I'm going to prove that that right-hand limit is 0. And you're going to see it's almost identical to how we do these other proofs. So let f of x be the square root of x, and let epsilon be any number greater than 0. Good so far?
Yes.
Okay. Observe that the absolute value of f of x minus 0 is the square root of x. Or the absolute value of the square root of x. Right? What am I trying to bound? Maybe remind you of what it is I'm trying to bound. I'm trying to get that x minus 0 is less than delta. I'm trying to find the delta that makes that true.
Right.
Or in other words, I want the absolute value of x less than delta.
Yes.
Right? What does my absolute value of x have to be less than in order to make so that the square root is less than epsilon? It's just going to be epsilon squared.
Right.
Because now if the absolute value of x is less than epsilon squared, then obviously the absolute value of the square root of x is going to be less than epsilon. So you could already see that. So then, if x minus 0 is less than delta, we need to show that that implies that f of x minus 0 is less than epsilon. So x minus 0 less than delta, that just means that the absolute value of x is less than delta.
Yeah.
Right? Those are both positive numbers, so take the square root of both sides. As long as we still have positive numbers, we're good.
It's not going to be plus or
So that gives me,
Also, when you square root it, isn't it plus or minus? Wouldn't it be plus or minus epsilon? If you define delta as epsilon squared, and you square root it, wouldn't it be plus or minus epsilon?
So I'm maintaining my inequality here. The positive square root of that is for sure going to be bigger than the positive square root of that.
Yes.
That's what we have here.
Oh, okay.
Good?
Yeah.
I have more information. I could also say that the negative square root of that is less than the negative square root of that, but I don't care about that information.
Okay.
So you're right, there is more information that we're not using.
Okay.
Okay, so now what does that give me? That gives me that the absolute value of the square root of x is less than the square root of delta, which is delta's epsilon squared.
Yep.
Which gives me that the absolute value of the square root of x is less than epsilon,
Yeah.
which is what we wanted. Because remember, that is f of x minus 0.
Yes.
So I showed that if x minus 0 is less than delta, then f of x minus 0 is less than epsilon. Therefore, as x approaches 0, f of x approaches 0.
Yeah.
Or the limit as x approaches 0 of f of x is 0.
The right hand.
For all x greater than 0.
Yes.
Why do we have to restrict ourselves to x greater than 0?
Can't square a negative.
Because you can't square a negative number. So therefore, if x is greater than 0, and x is less than c plus delta, remember in this case our c is 0, but we're saying x is between 0 and 0 plus delta. X is between c and c plus delta. You see that? Implies f of x minus L is less than epsilon. So these proofs are almost identical, you just add your restriction at the end.
Okay.
Okay? Alright. Couple proofs now. These are going to be more algebraic proofs. We're not going to be working with those epsilon and those deltas directly anymore, and it's going to feel like it gets easier.
Yeah.
Okay, so let's relax our thinking now with some nice, easier examples. We're going to find the limit as theta approaches 0 of sine of theta over theta. And we're going to prove that that's equal to 1.
Okay.
Now, before I do that, just a quick warning. Just because you're working with functions that you know and love doesn't necessarily mean that they have limits at points.
Okay.
Let me give you an example. Look at the function sine of 1 over theta.
Okay.
And I tried to graph that out for you. Here it is. As our theta gets really, really big, as our theta gets really, really small, our values jump really, really fast.
They oscillate a lot.
They oscillate a lot. So slow oscillations, fast, 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 around the y-axis. This is the y-axis right there, in case you can't tell. And then slowly stretch out again.
Now it looks like it's approaching 0.
A natural question might be, what is the limit of this function as it approaches 0?
But it doesn't have.
Yeah.
And it doesn't have one.
Is
So
that-
we already know 0 is a bad point. You can't plug 0 in because what's 1 divided by 0?
It's undefined.
Undefined. So you can't plug 0 into this function. But maybe it still has a limit there. Remember, just because a function is not defined at a point doesn't necessarily mean it doesn't have a limit there. Maybe it could have a limit there. And the problem is thinking about this, what value do we get really, really close to as our x values get close to 0? And there isn't one. We're jumping up and down faster and faster and faster the closer to 0 we get. There isn't one value that we're narrowing in on. So have to be a bit careful assuming that these limits just exist. Okay, and with that, let's calculate this limit. The sine of theta over theta, we're going to prove that the limit as theta goes to 0 equals 1. Now typically, for most points on most functions, you can just plug in the value and it works. Again, notice if you plug in 0 to this, what happens?
You divide by 0.
You divide by 0, it doesn't work. Can't do that, so we got to play with it. Okay, so for this proof, drew a quadrant of a unit circle here for you. So that's a 1, that's a 1. 1 in the x direction, 1 in the y direction. You with me?
Okay.
What is this distance right here?
That's your cosine theta.
That's just cosine of theta, right? What is cosine of theta? It's your x coordinate at some angle on the unit circle.
Oh,
What's the height of this? Sine of theta. What's this whole distance from O to B? 1, because it's a unit circle. Okay. Bit trickier question. What's the height from B to C?
1 plus cosine squared.
No, it's not going to be 1 because if I change my theta, it gets smaller. And if I lift my theta, it gets way bigger.
Yes.
So it's not some constant. What is it?
1 minus cosine squared.
Let's just call this h for a second. You with me?
Yeah.
Okay, so that is h. I know that tangent of theta. Is always equal to the y over the x.
Yes.
So it has to be equal to h over, what's this distance?
1.
1. So what does h have to be? H is the thing such that when you divide by 1, you get tangent of theta.
Yeah.
So what's h?
Tangent of theta.
Tangent of theta.
Right.
That's why we call this function the tangent function. It gives you the height of the tangent line. The line tangent to the circle.
Okay.
So. Oh, okay.
And intuitively, hopefully this kind of makes sense. As our theta gets steeper and steeper, our tangent shoots up. And what is the tangent at pi halves? Basically infinite.
Yeah.
And how tall would this edge of the triangle be if we made theta a 90-degree angle? It gets arbitrarily large as our theta gets arbitrarily close to 90 degrees. You see that?
Yeah. You can't ever reach.
Can't ever reach it. That was just intuition.
Right.
Okay, so there's our two triangles there. One more thing we need is a formula for calculating the area of this sector, is what I'm going to call it.
Oh,
You're
which
saying the curve.
The sector. That portion of the circle.
triangle?
No,
What's
using this curved
Oh,
edge.
just the curve
what's
part.
the
No, I'm going to outline what we care about.
Okay.
The area of this thing coming up, going down the curve of the circle, and back.
Okay.
I'm calling that the sector.
What-
The sector
can you define
OAB. Huh?
Define sector.
What?
What is sector? Is this
I'm just telling you, that portion of the circle.
so
The
it's-
sector OAB is that portion of the circle.
Okay.
We're not talking about triangle OAB. We're talking about sector OAB. What's bigger in terms of area?
Just sector.
Triangle OAB or sector OAB?
Sector.
Sector.
Sector, because it has this little extra area over there.
Yeah.
You see that?
Yeah.
Okay. What is the area for that portion of the circle? Another reason that we love radians is because it's something we can calculate like that. You probably don't see how to calculate it like that, but I'll help you see it. First off, what's the area of a circle in general?
Pi squared.
Just pi r squared, right? Or in other words, I'm going to write it in terms of 2 pi. So it's 1/2 times 2 pi r squared.
Okay.
That gives me the area of the whole circle, right? What would be the area of half a circle?
It would be 1/2 pi r squared.
It would be 1/2 pi r squared. Or it would be what you get if you plug pi into there.
Yeah.
Because pi-
What would be the area of 1/4 the circle?
1/4
4.
1/4. Or it would be what you get if you plug in pi halves into there.
Yeah.
Okay. Oh, okay.
You see it?
Yeah, I see.
So what is the area of a pi halves portion of a circle? It's 1/2 pi halves r squared.
It's just 1/2 theta times r squared.
1/2. So in general, the area of any sector of a circle is just 1/2 times theta times r squared if you use radians.
That's so cool.
One of the reasons radians are infinitely superior to degrees.
Yeah, that's awesome.
Okay, so now let's write some things out. Looking over here. Gonna start our derivation. The first thing I want you to notice is that area of the triangle OAB is going to be less than the area of sector OAB is going to be less than the area of the triangle OCB.
Right.
That's the first thing I'm going to say here. So observe that the area of triangle OAB is less than the area of sector OAB is less than the area of triangle OCB.
Okay.
Now let's just plug in formulas for each of those things. What is the area of this triangle OAB?
It is
Half the base times the height.
1/2 sine, or
What's the base of triangle OAB?
One.
it's 1.
1. We're not talking about this triangle. Forget that cosine there. That was just making sure you remembered your basic stuff. So we're looking at our triangle OAB. What's its base?
1.
1.
So it's 1 times 1/2 sine.
So what's the area of a triangle? So for this triangle, its area is half the base times the height.
1/2 times sine.
So 1/2 times the base times the height. What's the area of this sector? We already found out the formula for the area of a sector. It's 1/2 times your angle in radians times the radius squared. What's the radius of our circle? 1. So what's r squared? 1. So the area of our circle, our sector, is just 1/2 times theta, whatever the theta is. And then finally, that's less than the area of the big triangle, which is again half the base times the height. So it's 1/2 of 1 times tangent. So 1/2 times 1 times tangent. Or simplifying, multiply everything by 2, and we get that sine of theta is less than theta is less than tangent of theta.
Makes sense.
Yeah.
You with me so far?
I see that.
Okay. Now, I'm going to divide everything by sine of theta.
Okay.
Make sense?
Yes.
Yes.
Sine of theta divided by sine of theta is
1.
1. Theta divided by sine of theta is theta divided by sine of theta. Remember, tangent of theta is sine of theta over cosine of theta. So what happens when I divide that by sine of theta? The sines go out top and bottom.
1 over cosine.
And I'm left with just 1 over cosine.
Right. Okay.
Good?
Yep.
Okay. Now, common trick with inequalities, but remind you of it if you don't remember. I know that 1/4 is less than 1/3 is less than 1/2, right?
Yeah.
So if I flip the reciprocals of all those, it flips the order of the inequalities. That means that 4 is greater than 3 is greater than 2. So I'm going to flip the reciprocals, which flips the order of all my inequalities. What's the reciprocal of 1? 1. The reciprocal of that, that. The reciprocal of that, that. With me?
Yeah.
Okay. Now remember what we were trying to do. We were trying to figure out the limit as theta approaches 0 of sine of theta over theta. The reason we couldn't just calculate that is because 0 breaks this thing. Now I've rewritten it. Oh, I haven't rewritten it yet. We're okay. We're okay. Okay. So look to this side of sine of theta.
Yeah.
What's the limit of 1 as theta approaches 0?
It's 1.
1. As theta gets arbitrarily close to 0, 1 gets arbitrarily close to 1.
Yeah.
It is.
What's the limit of a constant? The constant.
Prove that.
What's the limit of 1 as, I don't care what you say. The limit of 1 as is 1. It doesn't matter as x approaches a billion or as y approaches a mountain. The limit of 1 is 1. The limit of a constant is a constant.
Yes.
Okay.
Okay. So we know that the limit as theta approaches 0 of 1 is just 1. What's the limit as theta approaches 0 of cosine of theta?
1.
Wait, say that again, sorry.
As theta gets really close to 0, cosine of theta gets really close to 1. Remember, it's the x-coordinate on your unit circle. As your angle is really close to 0, your x-coordinate is really close to 1.
So if both of those limits are 1, doesn't it?
So the limit as theta approaches 0 of this is 1. The limit as theta approaches 0 of this is 1. And this is sandwiched in between them.
So
Isn't
the
that
sandwich
the-
theorem says that.
So by using the sandwich theorem, the limit of that thing has to be between them,
Which is 1.
Which is 1.
which is 1.
Okay.
So therefore, by the sandwich theorem, the limit as theta approaches 0 of sine theta over theta is 1.
Yeah, but it
Then
can't
that
equal
does not
1
mean it's-
cannot equal 1.
Less than 1?
It's greater
Huh?
than or less than.
Is it supposed to be greater than or less than?
Yeah, because your 1 can't be 1.
Yeah, you're saying 1 is. Oh, it's the limit. It's not.
If this is less than, if this is greater than this is greater than this, then the limit of this is greater than or equal to the limit of this is greater than or equal to the limit of this.
Yes. Yes.
Okay.
So, yep. Squeeze theorem, I think, is what my real analysis textbook calls it. I think this textbook calls it the sandwich theorem. I'll probably accidentally call it the squeeze theorem because that's how I'm used to hearing it. Anyways, there we go. We proved it. Now let's use that theorem to prove a couple side theorems. These ones, much easier. We don't need any tricky trig. We can just do it directly. So now let's look at the limit as theta approaches 0 of this thing. 1 minus cosine of theta over theta.
Can't do that, can
You can't just plug in 0. So we got to rewrite it. And then hopefully, somehow we can get a sine over theta. And then that one we know how to evaluate. So, 1 minus cosine of theta over theta is equal to, I multiply it top and bottom by its conjugate. 1 plus cosine of theta. 1 plus cosine of theta. Same thing, top and bottom, didn't change it. Now, what's 1 times 1? 1. We have 1 times cosine of theta, and then negative cosine of theta times 1. Those two cancel out. 1 times cosine of theta is positive cosine of theta. Negative cosine of theta times 1 is negative cosine of theta. Positive cosine of theta, negative cosine of theta, those cancel out. And we're left with negative cosine of theta times positive cosine of theta is negative cosine of theta squared. See the algebra there? And in the denominator, what's theta times 1 plus cosine of theta?
It's theta.
It's theta times 1 plus cosine of theta. Okay.
Yeah.
Now, going back to our Pythagorean identities, sine squared plus cosine squared equals 1. Write that for you somewhere.
Yes.
You know that sine squared of theta plus cosine squared of theta equals 1. So if I subtract cosine of theta from both sides, then 1 minus cosine squared of theta equals sine squared of theta.
So we know.
So 1 minus cosine squared of theta, that's just the same thing as sine squared of theta. I didn't change the denominator.
Yeah.
You see that?
Yes.
Okay? Now, split it up. So I'm going to write my 1 sine of theta over theta. I'm going to write another one of my sine of thetas over 1 plus cosine of theta. Our whole goal here was to try and get sine of theta over theta, because that we know how to work with.
Right.
Good? And now, the limit of a function, the limit of a product, is just a product of the limits. So now I can take the limit of each of those pieces.
So 1 times.
So what's the limit? So in other words, the limit of what we started with, is equal to the limit of sine of theta over theta times the limit of sine of theta over 1 plus cosine of theta. Right? What's the limit of this piece? 1. What's the limit of this piece? As theta gets really close to 0, what does cosine theta get really close to? 1. So 1 plus 1, we get 2 in the denominator. What do we get in the numerator? 0. So we get 0 over 2. So you can think about it as 1 times 0 over 2. What's 0 divided by 2?
0.
Times 1? 0. So the whole limit evaluates to 0.
That's true.
Wait, why couldn't you have just? Why did you have to split it into sine of theta over theta? Isn't sine squared of theta?
So notice that we can't just plug in the 0.
Right.
All we were trying to do then, it was this thing in the denominator killing us.
Yeah.
we knew that if we could somehow associate that with the sine of theta, then now we know how to evaluate it. So everything I was trying to do was just make sine of theta over theta pop up as a term.
So you can get the 1.
And then that gets rid of the thing that's been killing us, which was that theta in the denominator.
Do you
So-
have to do that?
Huh?
Do you have to do that every time you get a variable in the denominator that will add to 0? Or-
If you have a variable in the denominator, like that, standing alone, and you're taking the limit as that variable goes to 0, you have to find some way to cancel it out. You got to make so that you're not dividing by 0 anymore, if you just plug in. Because you want to just plug in.
Yeah, you do.
All right, let's do another one. So, what is the limit as x approaches 0 of sine of 2x over 5x?
Well, you can't plug in 0.
Yep.
You can't plug in 0, but notice that that's almost exactly like this.
Yeah, it's very
We
simple.
almost have the sine of something over that something.
Yeah.
Really close, right? So it should probably come out to basically the same thing, 1, right?
Wrong.
I don't know. It's a sine of something going to 0 over something going to 0. This is a sine of something going to 0 over something going to 0.
Feels similar.
Yeah, so shouldn't it just be 1?
Should maybe be closer to 1. I don't know.
Let's find out. All right. So observe that sine of 2x over 5x is equal to, I'm going to multiply top and bottom by 2/5.
Just guys.
I'm trying to make my 5x into a 2x, so I have the same thing here and here.
Right.
How do I convert 5x into 2x? Multiply it by 2/5. But I can't just multiply it by 2/5 unless I do it in the top as well.
Yeah.
Otherwise, I've changed my number. Okay, so multiply top and bottom by 2/5. So in the denominator, now we get 2x. And in the numerator, we get 2/5. Right?
Yeah.
Pull the 2/5 out, and we get 2/5 times the sine of 2x over 2x.
Which is 1. The limit of that is 1.
Now, we're ready to evaluate our limit. So now the limit as x approaches 0 of sine of 2x over 5x is the limit as x approaches 0 of 2/5 times sine of 2x over 2x. And now we know from our limit rules that the limit of a constant times our function is equal to the constant times the limit of our function.
Yes.
Right?
Yes.
And what is the limit as x approaches 0 of sine of 2x over 2x?
1.
It's just 1. So we get 2/5 times 1. Or in other words, the answer is 2/5.
Pretty small.
So for anything like that, it would just be just 2 over whatever.
I wouldn't say that.
Yeah.
There's no reason for you to just quickly look at that and say, oh yes, 2/5.
Yeah.
In fact, 1 is a very reasonable guess. This piece is 2x is going to 0, 5x is going to 0.
Yeah.
How's that different than what's going on here? This is a sine of something going to 0 over something going to 0. They're both approaching 0. Turns out the rate at which you're approaching 0 changes the answer.
Yeah.
So, somewhat unexpected. Okay, let's try another one. Let's do the limit as t approaches 0 of tangent of t times secant of 2t all over 3t. Why can't we plug in our 0?
Because you'll get 0 in the denominator.
Because we have that 3t down there. It's that darn t that's bothering us. We want to somehow associate that t with the sign, and we'll be good. That's our goal here. Okay. So tangent of t times secant of 2t all over 3t. I'm just going to pull the 3t out as a fraction by itself, just to help us think. So we have 1 over 3t times the tangent of t times the secant of 2t. Just pull that out as its fraction out front. You with that? Okay. What is tangent of t?
It's sine of t.
It's just sine of t over cosine t. What is secant of 2t? It's just 1 over cosine of 2t.
Okay.
Good so far? Okay, I've got my sine of t here, so now I just need to rearrange my terms. I'll associate, I'll keep the 1/3 out by itself, put the sine of t over a t, and then we have times 1 over cosine of t times 1 over cosine of 2t. Right? Just write the product however you want, so that you know how to take the limit of each piece. Because the limit of a product is a product of the limits.
Yes.
So I just need to get the sine of t over t somehow.
Right.
And now we know how to eliminate it, how to calculate it. So then the limit as t approaches 0 of this thing is equal to what? What's the limit of 1/3?
1/3.
1/3.
1/3. What's the limit of sine of t over t?
1.
1. What's the limit of 1 over cosine of t? As t approaches 0?
1.
1. What's the limit of 1 over cosine of 2t as t approaches 0?
1/2.
1. As t gets really close to 0, what does 2t get really close to?
Oh.
0. And what's cosine of 0? 1. What's 1 over 1? 1. Or in other words, we evaluate to 1/3. And again, there's no reason that should have been, oh yeah, 1/3, I see it.
Yeah.
There it is. Okay?
Good.
All right. That ends today's lecture. Any questions? Okay. Yeah, that was a big one.